Welcome everyone to our October 2020 webinar. I'm Kelly Baber. I am the Energy Systems Engineer at Rutgers Case, which is the Field Managers for the IAC program. So just a reminder to everyone, keep your computers muted, and there are designated Q&A sections throughout the presentation. So then save up your questions, you can enter them in the chat bar, and then we will address them then. I think everyone here is familiar with the IAC program because you're all students and faculty, so I will brush over that. So it's about a 40-minute presentation with a Q&A at the end. And our next webinar will be November 5th, presented by the University of Utah's student lead on real-time optimization of multi-cell industrial evaporative cooling towers using machine learning and particle swarm optimization. And if you are interested in presenting a webinar, please feel free to email me. Here is my email address, and I will put it in the chat bar later for anyone who has any questions. Today's presentation will be presented by David from AMCA about minimizing fan system effect. So David, you can take it from here.
Okay. That's participation.
And Lisa will be talking about our PDH credits. And I'll allow her to discuss on that further.
Sure.
Okay.
Okay. Okay, can everybody see the screen? It says fan system effects. Nope, I have to hit share, sorry. All right. And Lisa, did the screen pop up?
Very nice.
Okay, so go ahead with the intro.
So hello, everyone. This is Lisa Cherney. I am the education manager for AMCA International. As Kelly had mentioned, our presentation today with Dave Maletich is fan system effect. And we, as you heard us mention, offer professional development hour credit for this. We are offering one professional development hour credit. We work through an organization called RCEP. This is a quality assurance statement that we need to put on screen so you know that this program is not endorsed by RCEP, but AMCA has met all the qualifications as a member of their organization to extend for education programs professional development hour credit. So today we do have one PDH available for people who view the entire program and then complete a post-webinar evaluation. Kelly has the link for that, and we can share that in the chat box as well. So again, just to remind you, you do need to stay present for the entire presentation and complete the evaluation afterwards, and you will receive an email with the PDH credit and a printable certificate. And if you have any questions about that, please pop some notes in the chat box and we will follow up with you. This presentation is copyrighted by AMCA International. So obviously reproduction, sharing, etc. is not allowed without permission from AMCA International. And then Dave, if you would like to go to your intro slide. So Dave Maletich is Vice President of Marketing at New York Blower Company. He has more than 29 years of experience adapting fans to various industrial, municipal, and power applications. He serves as an ASME AG1 Code Committee member for nuclear fans and is a member of several AMCA committees, including the DOE System Efficiency Task Force, the North American Marketing Committee, the Statistical Program Committee, and the Education and Training Subcommittee. In addition, David has presented fan seminars on various topics at the Industrial Ventilation Conference and also for professional organizations, including AMCA, ASHRAE, OSHA, and for other universities and consulting engineering firms. So with that, I would like to turn the webinar over to Dave Maletich.
Thank you, Lisa, for the kind words. Appreciate it. Again, my name is David Maletich. I'm honored to be here today. And what we're going to talk about is, in general, fan system effects and how systems or the ductwork that the fan is connected to changes or alters or can change and alter fan performance. It's a pretty high level presentation. So if you have questions, enter them in the chat box. I'd love to sit there and answer the questions as we're going through the presentation in the sections that we're going through. Or if you feel most comfortable waiting to the end, throw them in at the end. So what we're going to talk about is how fans are tested and rated, how ductwork configurations change fan performance and why. And then we're going to sit there and watch a video of kind of an actual fan in operation that we can add ductwork to it, take ductwork off, and see how it changes fan performance. Now, before we get started, let's first define a few key terms, and there's 3 key terms. The first is CFM, or the volume of air that the fan moves in terms of cubic feet per minute. And when we're talking about the amount of air that the fan moves, at standard conditions, each cubic foot weighs 0.075 pounds per cubic foot. Standard conditions, 70 degrees Fahrenheit, sea level, dry air. So if it changes from that, the temperature increases, we go up to elevation, we add humidity, that's going to change the density of the air. That's also going to change how much each cubic foot weighs. Now, when I first got started in the fan industry, 0.075, that's a pretty small number. But if you think of it as that's a little less than 1/10 of an inch per cubic foot, you put 13 of them together, you actually have 1 pound of air. And my car, mid-sized car, has a 13 cubic foot trunk. So everywhere I'm driving with that car at sea level, I'm driving around with 1 pound of air in it. So air does have mass to it. Second key term is static pressure, or the resistance that the fan has to overcome when moving that required volume of air. In the United States, we typically express it as inches of water gauge. You need 27.7 inches of water gauge to equal 1 PSI. It's a relatively small number. So to inflate car tires, you need to have about 900 inches of water to inflate your car tires to nearly 30 PSI. So just kind of giving you some reference there. And the last term is brake horsepower, or the energy that the fan consumes when it has to move that required volume of air at a specific pressure. So it's just how much horsepower is the fan consuming in order to do the work that's required. Now, here we have a fan in an AMCA accredited test lab. And I'm not sure if everybody's familiar with AMCA. AMCA is the Air Movement and Control Association. And it's basically the organization that gives all fan manufacturers that conform to AMCA a methodology for doing 3 things. That is testing the fan for airflow and pressure, testing the fan for sound, and finally, testing the fan for vibration. They give us the procedures on how to test the fan. That way, you as a customer or a user or a design engineer can go out and compare brand A to brand B to brand Z and have confidence that the fans were tested in the same way, and that test data means something, and that all the test data is the same. You don't have to sit there and add stuff to one test data to make it equal to another. It gives a common methodology. So looking at this fan in the lab, you notice a couple things. One is fan has an open inlet. Hopefully you can see my red pointer at the fan inlet, and that open inlet has a bell mouth to it. Purpose of the bell mouth is to allow uniform loading of the fan wheel, and secondly, to eliminate inlet velocity pressures. So basically it's a free open inlet and we don't have any obstructions at that point. On the discharge of the fan, straight run of ductwork. And that straight run of ductwork allows for the velocity profile of the air as it discharges the fan to even out. And we'll talk about that a little bit later. On the drive side of the fan, we see a motor that's powering the fan. A lot of people think that that motor is what we also record energy consumption with, because technically you can sit there and take voltage readings, you can take an amp reading. If you have a motor data sheet, you'll have an efficiency and a power factor that you can do a calculation with. But unfortunately, unless that motor is calibrated along with the VFD for the specific speed that the fan's running at, as well as the load conditions, those numbers are just estimates. They're not guaranteed numbers. In your horsepower calculation, will be off by as much as 5 to 8 percentage points. Most fan manufacturers utilize a torque metering device, such as a torque meter, to record the energy or the work that the fan does, and it's much, much more accurate. Behind that bulkhead, or where the fan is blowing through that ductwork system, is a large test chamber. And within the test chamber is a series of nozzles. And those nozzles are specifically how we calibrate that chamber for the fan that's being tested. If we have a little fan that's being tested here, most of those nozzles here are going to be open, or excuse me, closed. If we have a large fan, all these nozzles will be open. So we'll remove the caps off of these nozzles and allow more air to flow through that system. Any questions at this point as to how fans are tested or on any of the key terms? Okay, all right, moving on. What's a fan curve? Well, a fan curve is a graphical depiction for how a fan operates. And most fan curves are going to look like this, where you have pressure on the left-hand axis, flow is along the bottom, energy consumption is on the right-hand axis. And when we test a fan, we typically test first with all the nozzles closed, and we record the work that the fan does. This round dot here is our flow versus pressure dot. And the rectangular dot here is our energy consumption dot. So the fan with all the with the bulkhead nozzles closed off, pressurizing that chamber, is producing about 5 inches of pressure, consuming about 4 brake horsepower at 0 flow. And we just open up the nozzles, record the work that the fan's doing until we have enough points to create a curve. Now, we only have 4 points here. Typically, when we're testing a fan anywhere between 8 to 12 points in order to get a little bit more accurate fan curve. Now, when a person comes to us and looks at a fan curve, I've oftentimes been asked, where's a fan going to operate on that curve? Well, as fan manufacturer, we would state that fan can operate at any point along that curve. There's an infinite number of points that fan can operate at. So when a customer comes to us and says, hey, I need 10,000 CFM at 5 inches of resistance, what they're really saying is that they have a system that if you push 10,000 CFM of air through that fan, you are going to generate 5 inches of resistance. And there's actually, when you look at that system, there's a number of points that can represent how that system is going to perform. And just like with the fan curve, there's an infinite number of points. Now, not everything follows a system law. There's certain pieces of equipment like cyclones, pack tower scrubbers that have a little bit different characteristic. But in general, systems operate in this manner, in that if you increase flow, pressure changes by the square of the change in flow. So if you double flow, pressure goes up 4 times, or 2 times 2 is 4. If you cut flow in half, pressure will be reduced to 1/4 of its original number. And this is a graphical depiction of how a system is going to operate. So where the fan's going to operate is the intersection between that system curve and that our fan curve, and that point only. It cannot operate at any other point unless you physically change something in the system. So for example, if you have a damper and you close it, that's going to shift this whole curve to the left. If you have branches that are closed off and you want to open up some of the branches, that'll shift this whole system curve to the right. Conversely, if you speed up the fan, it'll raise the whole fan curve up the system curve. If you decrease the fan speed, it'll just shrink the whole fan curve down the system curve. But that's basically how fans and systems interact. And that's also what determines where the fan's going to perform on the fan curve and where the system's going to perform on the system curve. Any questions regarding fan versus system curves, or how fans are tested? Okay, so we're good on that. All right, let's talk about testing and rating of fans, which is actually a pretty important thing. Fans, at least in the North American fan market and in Asia, fans are typically tested in accordance with AMCA standard 210, which is also an ASHRAE standard. This gives us a methodology for how to test the fan. And again, just like I was talking a little bit earlier, that methodology is applied from fan manufacturer X to fan manufacturer Y. Fans are rated in accordance with AMCA standard 211. And this gives us an acceptance tolerance or criteria for that fan test. Basically what it states is if we want to have an AMCA certified fan, we would test a fan at our fan company, ship the fan and the documentation for the performance off to AMCA, who acts as a third-party validation organization. And they have to be able to represent our data roughly plus or minus 2.5% flow pressure, 5% on energy consumption. And if we do that, or they can do that, then we can certify our product. And that product will be certified for 3 years. What's to assure that over a period of time, over 3 years or up until 3 years, that a fan is going to maintain its fan performance. When we manufacture fans, we're working in a shop. We have lots of different shop workers. We have fixtures that are aligning blades, aligning various components. What's to ensure and make sure that that fan, 5 years, 6 years, 7 years down the line, is going to still perform as we originally cataloged it and as well as AMCA verified it. Well, basically, every 3 years, AMCA sends us a request to check test a fan. So let's say we have a class 3 fan that's been certified. AMCA will send us a letter, say, hey, I need to have a size 27-inch fan. Send it to me, and we're going to verify that that fan performance meets what your catalog rating is. Again, plus or minus 2.5% flow pressure, 5% on energy consumption. If we don't do that, if we can't meet it, then we risk losing our certification on that product, and then we would have to either drop certification or recertify that product. So it gives us a really good methodology for maintaining fan performance over the longevity of production of that unit. Any questions on AMCA performance or AMCA certification? Okay.
Dave, there is a question that came in.
Okay.
What method is used to interpolate from 12 points?
That's a good question. There is no guideline on that. AMCA does have, and basically what they're, let's go back to this curve. Okay. And basically, there's a methodology to interpolate between the various points, and that's what gives the curve shape. And you can use a cubic spline, you can use a polynomial least squared. Most, and correct me if I'm wrong, Lisa, most fan manufacturers use AMCA's curve interpolation program to interpolate between the points. And it'll produce something that's a little bit tighter fitting than a polynomial least squared curve fit program. Because I've been going back probably 25 years ago, we tried to experiment with using a polynomial least squared fit program, and it produced a smoother curve and missed points more so than what AMCA's program uses. But AMCA has a specific curve fit program that's relatively accurate. I shouldn't say relative, it's very accurate. And it does tend to sit there and go through each point pretty accurately. And that's what we typically use. Hopefully that answers the question. If you have further questions, just feel free to put that into the chat box. Okay, did that, testing rating. Okay, so when a fan's in the field, we've gone through all these procedures for testing a fan, making sure it's accurate. We have a third-party validation situation. Why do fans sometimes not perform as we catalog them? Why do they sometimes perform differently? And sometimes it's a little bit better, sometimes it's a little bit worse, sometimes it's way worse. What causes a fan to perform differently? Well, when we look at how a fan is tested, here we have an inline fan, here we have a centrifugal fan. Both fans have open inlets and they have a bell mouth at the inlet. Bell mouth guides the air into the fan uniformly, and we eliminate entry losses into the fan over a sharp-edged orifice. Discharge-wise, straight run of ductwork leading out of the fan into the test chamber. And that ductwork allows for the velocity profile of the air to even out. If we have a scenario or a situation where that installation is different than this installation, that fan may perform differently. Some ways to make the fan perform better. There's some ways to make the fan perform much worse. So on the discharge side of the fan, again, we talk about air. Air has mass. Mass wants to go along a straight line and wants to hug the outside of the volute shape of the fan housing. So when it leaves the fan, most of the air is at the top portion of the housing. Very little of the air is at the bottom portion of the housing. And unless you have the 100% of effective duct lengths to allow for that velocity profile to even out, you will not get full static pressure regain, and that fan will not perform as cataloged. And we'll see that in our video a little bit later. What is effective duct length? Well, if we look at the bottom here, for the first 2,500 feet of velocity, you should have 2.5 duct diameters. And for each 1,000 feet of velocity afterwards, you should have another additional duct diameter. So if you have 5,000 feet velocity, you should have 5 duct diameters. If you have 10,000 feet of velocity, you should have 10 duct diameters. If you have 1,500 feet of velocity, you should technically have 2.5 duct diameters. Now, the one thing I just want to mention in the graph is that at 50% here, you probably have about 80% of your regain. So having some ductwork is better than having no ductwork. So if you have some space constraints and don't have room for 100% of your effective duct length, if you can get 50% of it on there or something, you will get substantial amount of regain back. In fact, you'll get most of it during that first 50%. This last 50% is more of a polishing portion of it, and you'll get maybe 20% of your regain at that point. So it's good to have this amount at least as a minimum. If you have to have elbows, you have space constraints out in the field, some elbows are way better than other elbows. A position A elbow, really good. Air hugs the outside of the volute shape, continues along the outside of the elbow, and then you can have your straight run of ductwork afterwards to allow for static pressure regain. If you have your position C elbow, air hugs that outside volute shape, deadheads against the back of this elbow, has to get re-accelerated out. You will have some substantial losses with that. So if we look at some field pictures, we can talk a little bit about this. Here we have an upblast fan, throwing air upward. We have a position C elbow, so air hugs the outside of the volute shape. Deadheads against the position C elbow, has to get re-accelerated out. There's going to be losses associated with that. Don't have a straight run of ductwork after the fan. That creates a problem because we don't have any static pressure regain. So that's going to affect fan performance. Inlet side, we have an abrupt 90-degree elbow that creates a lot of turbulence of the air going into the fan. And if we look at the inlet size, this large disc or circle is the actual inlet size of the fan. They had to put an orifice plate here in order to contract this duct and adapt this ductwork to the inlet side of the fan. When this fan was tested afterwards, it was found to only be performing about 60% of its rated capacity, way underperforming. Here we have another fan. This is on top of a federal building. Again, we have a top horizontal fan with a position C elbow this time. Air deadheads, has to get re-accelerated out. And we have a rain hood at the discharge of the fan. Air deadheads here, it has to get bent down 180 degrees. This fan is not going to perform as cataloged. Here we have an industrial application, another position C elbow. Fans are top horizontal fans, blowing into this elbow, has to get re-accelerated back out and into the overhead plenum that's gathering air from each one of these three fans. I see a lot of position C elbows on the field, and that's how come it's so easy to get pictures of them. And I think a lot of it is because people just don't realize how much mass a fan moves. If you're moving 26,000 CFM through a fan, which is a medium-sized fan, you're moving actually 1 ton of air through that fan every single minute. So every That's 2,000 pounds. Every 3 minutes, you're moving 6,000 pounds of air through that fan. You're functionally moving a large vehicle through that fan every 3 minutes. That's a lot of mass. And just like if you're driving down a road, if you're driving down a twisty, turning road, it's going to take you a lot longer to get down that road. It's going to be less efficient than if you have a straight road. And if you have good bends in that road, that's going to improve the efficiency of that vehicle as it drives. And we have to remember that when we're moving air, we're not moving 0.075 pounds of air through a fan. We're moving, actually, we're starting getting into thousands of pounds, if not tonnage of air as it's moving through there. And we have to be cognizant of that. Here we have another guy. He's actually pretty proud of his installation. He was willing to pose for this. This is not a very good installation. There's the discharge of the fan, trying to sit there and adapt this large rectangular discharge to this round piece of ductwork. Air, again, hugs the outside of the blue shape, deadheads, and has to get forced back in through this piece of ductwork. This fan's, again, not going to perform as cataloged. Fan on top of a lab at an oil refinery. Very poor inlet box design, which we're going to see a little bit later in a video. Aspect ratio, depth compared to its width, not very good. Throws the air too high into the fan. Only utilize the top half of the wheel to move air. Bottom half of the air wheel, it's not going to see any air. It's kind of like having a snow shovel half filled. Expanded wire on the outlet, very poor. Recommend using kind of wire mesh much more than using expanded metal. And then we don't have a outlet duct for static pressure regain. I was walking through a parking lot in Chicago one day, leaving the ASHRAE trade show, and I saw these fans. I had no idea why they decided to use these types of hoods to try to keep rain out of the fan. I think some architect designed them, not a very good design. Rain typically falls at an angle. Sorry if there's architects out there. Rain falls at an angle, never, very seldom vertically. Doesn't take much of an angle for the rain to get back into the fan. No straight runs of ductwork for static pressure regain. They really don't serve any function other than they look kind of cute. Sometimes system effects are a result of design issues or design flaws. Here we have the clean air intake into the building. This fan is exhausting fumes from all the lavatories or bathrooms within the facility. When they started having complaints from the people inside the building, complaining about odors, they designed this nice little cowl system to redirect that foul air away from the clean air intake into the building. This is what happens when people buy cheap. This is a fan that was bought at an auction. Trying to force a fan to operate in an improper system is not a good idea. You may save a lot up front, but it's going to cost you down the line. Here we have an upblast fan. They use 50-gallon drum containers as a piece of ductwork functioning as a position C elbow, enforcing that air into the collector. General rule of thumb is I figure that every horsepower that a fan's operating or using or consuming for during a year for a fan that's running continuously costs about 600 horsepower. So if you're losing, let's say 10 horsepower because you have this improperly designed system, that's probably costing you about $6,000 a year in excess energy costs. So it's very easy to estimate what the payback of a horsepower savings is going to be over an improper design or a cheap initial purchase. This is not really a system effect, but this is a slide just to kind of remind everybody, centrifugal fans do move air in the proper direction, even if they're running backwards. When you're hooking up a three-phase motor to a fan, you have roughly a 50-50 shot of that motor running in the proper rotation. So you hook it up, you bump the starter, you should look and see if the wheel is rotating in the same direction as the blue shape or in the rotation arrow of the fan. But if you don't check it and you use your hand to feel air blowing out of the outlet, that's not the best way to do it. You're going to be wrong half the time. In this case, this is a fan that was used on a dust collector system. And the fan was able to move enough air to pick up dust at the source, but it wasn't moving enough air to keep that particulate entrained in the gas stream while the fan was in operation. So all that dust dropped out of the ductwork, dropped all into the fan, and it creates a huge housekeeping issue, a huge safety issue. That ductwork was never designed to support that kind of mass load. And so consequently, they're at risk of that ductwork collapsing in the middle of the facility. So safety-wise, it's very important to make sure the fan's rotating in the proper direction. Not all systems are bad. Here's actually a very good system. Here we have a fan exhausting from a facility, has a silencer on the inlet. Silencers are great because it prevents or minimizes transmission of noise from the fan back into the factory. Also acts as a nice straight run of ductwork so that we don't have any losses that are affecting how the fan performs. Rectangular round transition on the discharge, nicely tapered, it's not too abrupt. Straight run of ductwork, and then we have what we call a no loss rain hood at the discharge of the fan that does two things: prevents rain from getting back into the fan, and there's no losses associated with this appurtenance during performance. So it's a really nice device for discharging air to atmosphere and not having any losses associated with that fan. Any questions that have come up to this point on system effects? Okay.
Yeah, I've got a quick question just about static pressure regain.
Yes.
If you can revisit the importance of static pressure regain for efficiency and performance.
Okay. Okay. If we look at this picture here, static pressure regain is it's very important if you want efficiency of the unit and you want the fan performing at its best. If you don't allow for static pressure regain, basically you're going to lose a velocity pressure at the fan discharge. And velocity pressure is simply your velocity divided by the quantity, your velocity divided by 4005, that quantity squared. And so if you're moving air at 4,000 feet per minute, you're going to lose 1 inch of static pressure by not allowing for static pressure regain. If you're moving only 1,000 feet per minute, it's not quite as critical because it's a squared value. So it's going to be 1,000 divided by roughly 4,000 squared. So that regain is going to be much less. If you're moving, but the faster the velocity, the more pressure you're going to lose from that fan during operation. And that pressure is just, it's lost forever. It's, you're not going to be able to get it back. And other than you have to run the fan faster, running the fan faster means that you're going to consume more brake horsepower and your energy costs are going to start going up that way. Does that answer the question?
Yeah, it does. Thank you.
Okay. Okay. Moving on, we are going to watch a video on system effects. This is very similar to the reason why we created the video. We were at both Amka and I were at the AHR Expo in Orlando. We wanted to do a live system effect demo, but the conference center wouldn't allow us to do it. So we created the video. It's broken down into little sections. So we're going to look at inlet configurations, such as elbows, corkscrews, straight run of ductwork, inlet boxes, etc. And we're going to have little question answers after each little section. And the nice thing about the video over here is we were going to try to do it live, but it's hard talking loud enough over the fan during the presentation. So I think hopefully the video works out better than an actual live presentation. So let's move on.
Now, we've oftentimes
sorry about that. Okay. Hopefully everybody can hear that.
Yes.
Hello, my name is David Maletich. I'm with the New York Blower Company. I'm Vice President of Marketing. And today we're going to look at system effects, or how inlet and outlet discharge configurations change fan performance. And you'll see by adding different inlet configurations, it'll have a direct effect or change in the fan's operating performance. Before we get started, let me just explain a little bit about how this fan is configured. First, the fan has an open inlet that allows the air to uniformly load the wheel. And we have a straight run of ductwork, just as the fan gets tested at AMCA, to allow for the static pressure to regain before it goes out to atmosphere. So the first thing we're going to do is we're going to grab a piece of ductwork. It's a 90-degree elbow, and you can see there's no vanes inside the elbow, and we're going to see how it affects the fan's performance. So we put it on the fan's inlet, and looking at the magnehelic gauge over there, you can see that the fan performance has gone down significantly just by putting a 90-degree elbow on the inlet of the fan. What's happening is air has mass, and when anything has a mass to it, it wants to go in a straight line. So the air enters this duct uniformly, it wants to go straight down to the bottom, and then it has to bend 90 degrees into the fan. So basically what we're doing is we're loading the bottom half of the fan wheel as it's rotating, but the top half of the fan wheel doesn't get any air, so we're not fully utilizing the mechanical aspects of this fan. Now the next thing we're going to do is we're going to add an elbow, take off this one here, and we're going to add an elbow that has a turning vane in it. And that turning vane basically splits the duct into two sections. So when we put it on here, look at the magnehelic, you'll notice that there is still a loss associated. However, that loss is much less than what it would be if we had an elbow with no vanes in it. So again, air comes in, loads this uniformly. However, instead of the air going to the bottom, this vane forces the air to turn in two sections. So now we're better utilizing the mechanical aspects of the wheel as it's rotating.
Okay, any questions on an inlet valve or inlet or an elbow or an elbow with a turning vane at the inlet of the fan? Okay, we'll move on to the next section, which is corkscrews.
Now, we've oftentimes seen installations of fans where you have a wall here, and so you don't have a whole lot of space in order to run ductwork into the fan. And what we're going to do is create a corkscrew and see how corkscrews affect the fan's performance. So put a 90-degree elbow on the inlet of the fan, and we're going to sit there and put it on in this direction here. Now basically, when you're looking at this, you have to also listen to it audibly, because what you're going to hear is either the vibration and the fan noise go up or down. Now in this case, air is coming in this direction. It wants to go into the corkscrew, so it's starting to pre-spin as it goes through the fan. Pre-spinning of the air means that the wheel or the air is going in the same direction that the wheel is rotating, and the air cannot get moved as efficiently as what it would be if it was coming in straight and laminar. And that results in a fan that's quieter, but also when you look at the magnehelic gauge, you'll notice that the static pressure generated by the fan went down pretty significantly. Now when I turn this 180 degrees, you'll notice that, like I said, kind of listen to what's happening, is that I put it on here, the fan gets much noisier, sounds a little bit rougher, and also the magnehelic is showing the pressure went up as the fan's operating. So that extra noise is basically, we're now counter spinning the air as it enters the fan. Air is going in the opposite direction of the wheel rotation, kind of like how when you're, if you're rolling down the driveway backwards, put your car into gear, push it forward, it effectively moves, but it does it in a very rough manner. Same thing happens with the air as it enters and discharges the fan. So if we were actually able to take an amp reading and do an efficiency calc, even though this fan's producing more pressure, it's doing it much less efficiently. Horsepower has actually gone up, and that's kind of evident in the amount of noise that the fan's producing.
Any questions on corkscrews before we move on to inlet boxes?
We did have a question in the chat box. Someone asked, how small can this demonstration be? For instance, could it be built as a tabletop demonstration, or would that be too small? Also, what is the horsepower of the fan in the demonstration?
That's a good question. This is functionally almost a tabletop demonstration. Most of the time when I'm doing it, I will actually do this on a table, like just a bench table in front of a group. But it could actually be made smaller than this. That believe, if my memory serves me right, that's either a 3/4 horse. I think it's a 1 horsepower motor that's on that, and it could be made smaller. You could probably make it half the size. The important part is to make sure that the elbows have a relatively sharp gore to it, or sharp turn to it. I've done the presentation with large radius gores on it, and it doesn't show off the effects quite as meaningfully. Okay. Moving on to inlet boxes.
The next thing we're going to add to the fan is an inlet box. Here we have an inlet box, and as we saw in the presentation earlier, there's certain aspect ratios that you want to have with an inlet box. This one's a very poor aspect ratio. It's very short in this direction compared to its width, which is very long. It's a very rectangular inlet box. We'll put this on the fan and we'll see what happens. Okay. Notice that the fan's doing a couple different things. One is efficiency, or the amount of pressure that the fan's generating, went down significantly. It's almost half as much as what it was originally. Second thing you'll notice is that that needle is not very stable. It's going up and down. This inlet box has actually put the fan into a surge condition. And those surge conditions on a small fan are pretty bad in that, one, it creates a lot of noise. It goes up and down. And then secondly, what you'll notice is that if you have an application where you need smooth laminar flow going through it, like let's say a combustion air system, it's very hard to maintain a constant flame when the air is going up and down pretty consistently. The other thing that having a fan left to peak is when the fans get very large, like you have a 2, 3, or 1,000 horsepower fan, that vibration can become pretty significant and actually cause ductwork to crack, can also cause foundations to crack. Now here we have an inlet box that's a little bit better designed. Its aspect ratio is much more square. Its depth compared to its width is much more on the square side of things. It's not an elongated rectangle. The other thing you'll notice is that we've added turning vanes to this inlet box. Turning vanes, just like with the 90-degree elbow, help efficiently load the air as it goes into the fan. Put this onto the inlet of the fan, and you'll notice that, yes, we do have a loss associated with the inlet box, but it's much less than the improperly designed inlet box losses.
Any questions on inlet boxes before we move on to straight runs of ductwork at the inlet of the fan? Okay.
Now the next piece of ductwork I'm going to add to the fan is just a straight run of ductwork. You can see that it's just a long tube, and there's nothing inside of the tube. It's just a very hollow piece, and we're going to see what happens. Putting this on the fan, you'll notice that there's a loss associated with this straight run piece of ductwork. And that loss is actually relatively significant. Now, a lot of people think that that's associated with friction loss through this ductwork, the amount of effort that it takes to pull air over a piece of sheet metal or a piece of Schedule 40 pipe. Now, if we add this venturi to the inlet, just a plain venturi, see what happens. You'll notice that almost all the losses associated with the straight run of ductwork are gone, that there's virtually no losses. And what you soon realize is that those losses are associated with the entry loss over this sharp-edged orifice. And that entry loss is pretty significant, almost 1/10 of an inch. By putting this venturi on the inlet, you've eliminated almost all of those entry losses associated with that. And we can watch the magnehelic again.
Any questions on straight runs of ductwork before we go on to corkscrews at the beginning of a straight run ductwork and vortexes?
Now the final thing I want to show you is corkscrews. And the problem with corkscrews is that corkscrews can go down a piece of ductwork for an extended period of time. The fan itself wants to create a venturi or a vortex as the wheel rotates. And if we create a vortex over here, that vortex will continue down that straight run of duct. And if you look at the magnehelic, you see that the losses were almost the same as the losses we saw in the first part of the video when we put the corkscrew right at the inlet of the fan. And that's because that air wants to pre-spin all the way down the duct, because the fan's creating a pre-spin, this corkscrew is creating a pre-spin, and there's no place for that pre-spin to go away down this ductwork. Now the only way to eliminate that is to put perhaps a T or a cross section in the duct known as a vortex breaker to help break that vortex and prevent that pre-spin from continuing from here all the way into the inlet of the fan.
Okay, any questions on vortexes in ductwork and fans?
We have another one from the chat.
Yep.
Would you be able to demonstrate the fan laws with this demonstration as well as the system effects if you had a VFD?
Ooh, I've done this presentation with somebody that I was in Australia and they set up with a VFD. You have to learn the system effects demo with the new system, but you could show, yes, you could definitely do, you could show off a pitot tube traverse. You can sit there and show off how you do a fan curve. You can show off the changes in the fan curve as you increase or decrease the fan speed. And you could also show how the fan curve shape changes as you put on different ductwork configurations. You could actually make this a whole 1 day or 2 day course on just curve shapes, system effects, and fan laws, etc. And with the simple addition of a voltage meter on the motor. So yeah, absolutely, you could do that. And if you want to talk about this afterwards, I can probably work. This has been on my bucket list of things to do for 25 years, but it's something I definitely would love to do. And I could give you some advice on how to do it. So hopefully that answers the question.
I believe it did. Thank you.
Okay. Now we're moving on. Hopefully I'm right. Now we're moving on to the discharge of the side of the fan. A lot fewer system effects on the discharge side, but discharge is equally as important as the inlet
Now we've
side.
completed all the different configurations we can put on the fan's inlet. So we're going to disassemble the unit. We're going to move the readout device to the inlet of the fan, and we're going to see how changes in discharge configurations also changes the fan's operating performance. As you can see here, we've moved the measuring device, the pitot tube, to the inlet of the fan, and we're going to measure or examine how fan performance changes when we add or change the ductwork configuration on the discharge side of the fan. So the first thing we're going to do is we're going to add a straight run of ductwork to the fan. The straight run of ductwork allows for the velocity profile to even out as the air discharges the fan. And what I mean by velocity profile is when we take this piece of paper here, just a normal 8x11 piece of paper, put it at the discharge of the fan, notice that the air actually is negative pressure here and actually sucks the piece of paper into the fan. And if I put it on the other side of the volute shape, it's positive pressure and it actually blows the piece of paper upward. So as air discharges the fan, it's not laminar across the whole discharge, it's all focused on this section of the fan. Putting this ductwork on the outlet of the fan, notice that there is a change in performance when you look at the magnehelic gauge, that it's actually dramatically improved. And the reason it's improved is that the air velocity profile has gone through this piece of ductwork has actually evened out. So if I look at it here, put the same piece of paper here, notice it blows the piece of paper up. It's no longer negative pressure at this section. And if I do the same thing at the other side, it's positive pressure as well. So now we have laminar flow, and that laminar flow results in increase in performance. Now when you have a straight run of ductwork, you want to have the proper length, which is typically 3 duct diameters for the first 3,000 feet in velocity, and an additional duct diameter for each additional 1,000 feet in velocity. However, it's better to have something rather than nothing. So if you're space constrained, it's good to have a short piece of ductwork rather than no piece of ductwork. So if we take this rectangular round transition, the same one that we used when we were doing the inlet measurements, put it on the outlet of the fan, and again, no turning devices inside of it. Put it on the outlet. Notice that there is, again, an increase in performance when we look at the magnehelic gauge. And if I take the same piece of paper, notice that even in this short distance here, we've already started to get some evening out of the velocity profile. No longer is the pressure negative on this side. You can see it's blowing the piece of paper up. And it's starting to even out on this side. It's not as harsh as what it was as the air was discharging the fan.
So any questions on discharge ductwork before I think we're moving on to the final little snippet of the video, which is discharge elbows. Okay, moving on.
Now oftentimes you have to have an elbow at the discharge of the fan. And if you have an elbow, like this 90 degree, there's a proper way to have the elbow orientated and there's an improper way. The improper way is to put it where it breaks the back of the air. The fan has a volute shape. Most of the air discharges on this side of the housing or the outside of the volute shape. And if we put an elbow that breaks the volute shape or goes against it, air pressurizes here, gets deadheaded, and has to get reaccelerated back out. So if I put the elbow on this way, notice the performance is decreased when you look at the magnehelic gauge. Now if I take that same 90 degree elbow, turn it 180 degrees, and now the outside follows the volute shape, you notice that there's very little change in performance when we look at the magnehelic gauge. Then we can put our straight run of ductwork here. It'll allow the velocity profile to even out, and we can get our static pressure regained with very little loss. Thank you very much for watching. Hopefully all these configurations that we use to configure inlet and outlet ductwork helped answer your questions as to how ductwork changes fans' operating performance. If you have any questions, feel free to contact us at AMCA, the Air Movement and Control Association.
Okay, before I kind of go on to the little final snippet of information, just go through some quick facts. Always get upset with me, but I love to sit there and give little fonts of information. As I went through on the presentation, if you're moving 26,000 CFM of air through a fan, you're approximately moving 1 ton of air a minute. And I think this is where people get in trouble, is they just don't realize the mass flow that's going through the fan. It is pretty significant. And if you double it, you're moving 2 tons of air through the fan a minute. So it's a pretty significant number. 4,000 feet per minute velocity, which is the minimum conveying velocity for most materials. Like if you have a dust handling system, you're moving sawdust or other fines through the fan, you typically want to run the air through the system at 4,000 feet per minute. You're moving air through the fan at roughly 45 miles per hour. So, if you have a pickup truck or a car and you're driving through a straight road, you typically are going to get there much more efficiently, much quicker, and with much less energy costs than if you decide to pick a curvy road, especially one with some abrupt 90-degree turns and stoplights. As I mentioned, 27.7 inches of water equals 1 PSI. So inches of water is a relatively small number. It takes about 900 inches of water to fill up a car tire. And for estimating purposes, and this changes widely depending on where you live and your energy costs, but I usually figure a fan running 24/7, energy cost is about 1 brake horsepower for 1 brake horsepower is roughly $600 a year. So it's a quick, easy way to sit there and see how much energy savings can help versus initial first cost. At this point, I'd like to answer any final questions before everybody gets to go to their next class or their next obligation. Kelly, Sarah, any other questions, or are we good to go?
There is one question, Dave.
Mhm.
This person says, I often see two terms in fan specifications, external SP and total SP. What is the SP x-axis mean on a fan curve, ESP or TSP? And then there's a follow-up to that. Also, what does the y-intercept show? The TSP of the fan? Do manufacturers take into account for this system effect loss when they mention TSP in specifications?
Okay, that's a good question. It's because I have not heard what was that one, ESP?
ESP or TSP?
I've seen TSP, you see SP, and you also see TP. Total pressure, ideally, to be honest with you, 9 times out of 10, fans should, probably 99 times out of 10, 100, fans should really be selected for total pressure, not static pressure. And basically, total pressure is static pressure plus a velocity pressure. And when you're doing system calcs, oftentimes when you're doing system calcs, you're doing not just a static pressure calc, but you're also adding velocity pressure for friction loss through the duct at various points. So if you're selecting static pressure versus total pressure, you're tending to oversize the fan 1 VP or 1 velocity pressure, or your velocity pressure calculation that's there. Static pressure versus total static pressure also has, and I can't remember the exact term, I have it somewhere, I could find it and send it off to the person who's asking the questions or off to everybody. But that also has to do with a velocity pressure, and basically total static pressure is kind of like a static pressure rise through the fan calculation, and tends to be a little bit lower in overall fan performance than a static pressure reading. So if the person can eventually share their information with Kelly or Sarah or yourself, Lisa, I can send them what is included in a SP rise in a total pressure calculation and where the VP is taken out of them in each one.
Great.
All right. I'm just going to share that one more slide to remind everyone about the PDH credits and the survey.
Okay.
Sorry, my mic failed when I was reading off that question, so I guess you guys did not hear me.
Okay.
All right. So here's Lisa's information if you would like to email her with any questions. And the link is right here, and it's also in the chat to fill out the survey.